Welcome back. As per my promise, I did say that in this part 3 of our functions video series, we are going to be diving deep into linear functions. But before we get deep, let's just address the basics that we need to be familiar with, the basics that we are going to be using to analyze, sketch, and determine the equations as it specifically relates to linear functions. Now, before I get into what makes a linear function, I need you to get a few things straight. At this point, I know for a fact that you've done this for at least 2 years now, seeing as linear functions. It's a topic that starts being covered from the lower grades, ergo grade 8 in this case. So it is my belief, in my experience as a tutor, that at high school level, at this FET level, learners usually find this ridiculously simple, seeing as it's something they are quite familiar with, and it's, well, linear functions in and of themselves are the most ridiculously simple functions in all of the types of functions that you're going to be assessing. Now, first things first, whenever you are dealing with any type of a function, the key or the core of the matter, the heart of the matter, always starts with the standard form. Now, when dealing with linear functions, our standard form takes the format of y is equals to mx plus c, where c is a constant and it represents the value of where the graph cuts the y-axis, and then where x is just our x variable, and then this m in here is our gradient. Now, when talking of the gradient, what are we talking about? Essentially, we are talking about what determines the slope of our graph, which then brings me to my point. The gradient of the graph determines the shape of the graph. If our gradient is positive, we have a sketch that looks pretty much like this one in here, where our graph increases from left to right. This, I believe, it's something you are already familiar with from the lower grades. And vice versa, if our gradient is negative, we would have a slope that is decreasing as we go from left to right, as the case in the second scenario in here. Now that we've mentioned that, now that we've gotten a firm grasp of what the standard notation denotes of a linear function, then I need to bring you into the two types or the two equations we have for calculating the gradient of a straight line. One formula is this one in here, where in this formula, this is the one we use when we have we know 2 points on a graph. Says, for instance, in this first graph, we know this point in here, and then we also happen to know the coordinates of this point. If we know the coordinates of any 2 points on a graph, then we can use this formula, because if you and I were to pay attention just a little bit, according to this formula, this in here, y1 and x1 are the coordinates of 1 point. So if this is our point 1, then for y1 and x1 we will be substituting the coordinates of this point in here. And for y2 and x2, they represent the coordinate of yet another point. So if this is our second point, then for y2 and x2, we will be substituting the respective coordinates of such a point. It applies to any type of a straight line function. Now, you may be asking, what happens if I'm not given the 2 points on a straight line and I want to determine the gradient of a line anyway? Then you have another equation where you are given m is equals to tan theta. This is one of the equations you can use, but I'm not gonna dive deep into this one for now. I'm just gonna mention it in passing. There's gonna be a part where we're gonna be dealing with this in depth, at which point I will more than happily exercise or the discretion of going into depth in explaining how to use this formula and where to use it. But for the interim, you and I are gonna be dependent strictly on this equation in here that uses the 2 points on a straight line to determine the gradient of a function. Needless to say, nothing has changed. Functions still represents the relationship between the inputs and the outputs, meaning the relationship between x and what? X and y. You said it right. And we also ought to remember that between this x and y, we are always going to have the rule. Now bear in mind that as it specifically relates to linear functions, our rule is always going to come in the form of mx plus c. mx plus c. Do pardon my rather ugly handwriting. I do write like doctors, guys. But anyway, that's what I need you to denote. So we are going to be expected, or we are going to be dealing with different scenarios when handling functions. One scenario is going to be where we are expected to actually sketch a graph of that particular function. The other scenario is going to be where we are given a graph and expected to determine the equation and perhaps other information with respect to such said graph, right? So enough said. Now moving on to the next part of our introductions to linear functions. I've just mentioned that the slope or the gradient determines the shape of our graph, right? When the gradient is positive, our graph increases from left to right, and when the gradient is negative, our graph decreases from left to right. But then what happens if the gradient of a line is parallel to the y-axis, as we have in this case in here? This line in here is parallel to the y-axis. When the gradient of a line is parallel to the y-axis, the gradient of that line is undefined. It is undefined. A line that is parallel to the y-axis has a gradient that is undefined. In other respects, I am saying to you, the gradient of the y-axis is undefined itself, right? That's that. Now I'm gonna be switching on to the scenario where the graph is parallel to the x-axis. When a straight line is parallel to the x-axis, its gradient is equal to what? 0. It's equal to 0. So to repeat, when a line is parallel to the x-axis, its gradient is equivalent to 0. This simply implies that for the x-axis itself, its gradient is equal to what? To 0. So that is to say, seeing as the gradient of the x-axis is equal to 0 and the gradient of a line that is parallel to the x-axis is also 0, that simply means when two lines are parallel, their gradients are equal. By the same token, let's look at the case of the y-axis and the line parallel to it. The gradient of a line parallel to the y-axis is undefined, just as the gradient of the y-axis itself is undefined. That also confirms what we deduced from the first scenario, that when two lines are parallel, they have equal gradients, right? So that is what I need you to take in as far as the introductions to linear functions is concerned, right? So I didn't mention anything with respect to what happens if lines are perpendicular with respect to sketching and all of that. So that is food for the next parts of our video series. Now in this next part of our video series, which is part 4, I am going to be going into the gradients of perpendicular lines with respect to the gradient of parallel lines, and then from there we are going to be getting into the sketching of functions. Thank you very much. See you in the next video.